This is going to be tough for me because I am taking what is normally 4 hours worth of material and shoving it down to 45 minutes. I'm giving you sort of the basic primer on microscopy and photomicrography, which is taking pictures through the microscope. A couple of basic, well, everything here is basic, but we're going to be talking about transmitted light, just to make sure everybody has definitions down. Transmitted light, straightforward. It's light literally going straight through something. Reflected light bounces off. Think of a mirror. Refracted light, that's light that's bent as it goes from one material into another. So transmitted, reflected, refracted are just common terms that we use a lot, and that's what they mean. Here is your, in air quotes, typical microscope. Basically what we're dealing with is your oculars or eyepieces up at the top. You've got a binocular or a trinocular head. Trinocular with all of these because the third part is where the camera goes. You're going to have some kind of a beam splitter that's going to send the light either to the eyepieces or to the camera, or both, depending. We have different options. One of the reasons that I'm doing all this is you have to understand what all the basic parts are, and then you sit down at a microscope and say, oh, where is that beam splitter? And you can kind of figure it out based on taking a look at things. So as a for instance, in the upright scopes, it's going to be fairly straightforward. It's going to be a little slider about there that comes out. But on the DMI-8, hey, guess what? You got to push your finger on the little LCD screen in front and look for the software interface and push it there. So it doesn't really matter where it is. You just need to know, oh, I need to find the beam splitter. All right. So that's the point, though. If you don't see anything through the eyepieces, but you see it on the camera, you got it. The objective lenses are held on something called the nose piece. You rotate the nose piece, do me a favor, and grab the nose piece when you turn it, if you have to turn it. Again, the DMI-8, you can pick it, with using the interface instead. But if you're turning it, don't grab the lenses so much, because if you're squeezing the lenses, you can loosen them and do other things to them. So better to grab the outer collar of the nose piece. Specimen stage is pretty straightforward, and there's usually a little XY control off to the side. Underneath the stage, you've got the substage condenser. The condenser is made up of basically 3 parts. You've got your condenser lens. Some microscopes have like a flip-in lens, some don't. There's an aperture in there as well, so an iris. So you're going to open and close that thing. We're going to be using that. And underneath, hopefully, you're going to have centering screws as well. So these are things that are going to come to the fore when we use Kohler illumination, which if you don't know what it is, you will when we're done with this. Now, over here we got our focusing knobs, and this is important. You've got your specimen focusing knob, which is generally going to move either the stage up and down or the eyepiece or the objectives up and down, but it's basically going to focus your specimen. You got a coarse and a fine usually. And so you're moving it and you're focusing through your specimen, not to be confused with the condenser focusing knob, which is going to focus what? A condenser, right? So that moves the condenser up and down underneath, all right? And so we're going to need to use both of those. At the bottom, you've got your field diaphragm. And the field diaphragm, again, is another aperture iris that opens and closes, and we're going to use that. There's going to be a power button someplace, which brings our light in. So this is your basic upright, bright field kind of concept. All right, and we're going to build on this. All right, now, here we go. We got objectives above the stage. That's what makes it an upright scope. All right, so if the objectives are on top, you've got an upright configuration. This is generally used, not always, for slides. So if you have little glass slides and you're putting them on it, you're going to put it on the stage, and the light path is going to start back here with your transmitted light, transmitting straight through the condenser, through your specimen, up to the cameras and the eyepieces. That's the path. Right? This is the light source. So again, if you take that picture before and ignore the fact that there's a picture of a microscope there and look at the parts, you've got your light source. After the light source, let me back up a second. Right in here on this particular picture, there's some filters. All right, we're going to use some of those filters maybe. We'll talk about those. There might be some filters thrown in the light path. Then it goes through the field diaphragm. Then it goes through the condenser aperture in the condenser. And then it goes through the specimen and then through the objective to the beam splitter to either your eye or the camera. Now, this is an inverted microscope. Why is it inverted? Because the lenses are underneath the stage looking up. Generally used if you've got cells in dishes and things like that, because you can't say, oh, what's in here? Oops. Yeah. So you put the slide on the dish on the stage, and then you're looking from underneath. So different setup. But guess what? If you look at the light path, it's exactly the same. There's no difference. We just took it and turned it upside down. So now the light source is at the top, and everything goes right down through until you get to the camera or the eyepieces. All right, so you can find all the parts on either of these types of scopes just by kind of following where things go. All right, so oculars. Most of the oculars or the eyepieces are going to have some kind of a diopter on them. A question you get a lot of times is, should I take my glasses off? Basically, you can if you want to, but you don't have to, unless the only exception to this is if you have astigmatism. If you have astigmatism, your glasses are correcting for the astigmatism, in which case you need to leave them on. If you don't have astigmatism, then whatever's comfortable for you. The bottom line is you can adjust the diopter on each objective to your specific eye. So it's just like twist it this way or that way, depending, so that you want to look through both eyes, both open at the same time, looking at your sample. The point here is in the good old days of film, you took your pictures and you had to be absolutely sure that you were in focus based on what you could see through the eyepieces, because you didn't get your pictures back until you developed them and printed them and did all that stuff, a couple days, along the line, maybe the same day if you're fast. But you didn't have another chance right now. Now, of course, we see everything live. And so what you're really going to do is put your sample on, get everything set up, send the light to the computer, and you're going to see your image live. All right? So you get the image live, you focus on the screen, and then you turn back to your oculars and adjust the oculars to match the screen, because the screen's what matters. That's the picture. What you see through the eyepieces is irrelevant. So as I said, there's going to be some kind of a beam splitter. Sends the light either to the, this is the trinocular head I was talking about, either up to the camera or to the eyepieces. So one general rule, that this picture is breaking, except that actually this is an action shot. I'm actually turning it, right? Always start with the 10x objective in place. Doesn't matter what microscope you're sitting down at, except the stereoscope. Always start with the 10x. So, and you can kind of see the reason here. This is the 20x that's in place right now. They're color-coded, so basically wherever you see that yellow bar, that's the 10x objective, okay? And that works across all manufacturers. A 10x has a very big working distance. That's the distance between where you're in focus and where the lens is, all right? Big space. 20x does not. If the lens, if the specimen stage is up too high and you bring in the 20x, you're going to smash your slide, all right? It's an awful sound. I've only heard it once in practice. You start with the 10x lens, and what I show them is I can turn the focus up and down like this, and I don't even look at it, because it will not come up and hit the specimen or hit the objective. There's too much working distance there. So always, always start with the 10x. Once it is in focus at 10x, the rest of the lenses are going to be parfocal, meaning they're about in the same plane of focus within a little twist of the fine focus knob. But basically, you start with the 10. And again, grab the knurled ring here of the nose piece rather than the lenses when you move them. On any objective, there's a bunch of things on here, and they all mean something. And I can't tell you everything, but I'll tell you the major things. So first of all, they're going to tell you a lens type. So in this one, it's a plan floor. Plan meaning flat field. If you're taking pictures, you want a flat field lens. You want a plan lens. Floor really means it's kind of designed for fluorescence work, so it's got better transmission and things like that. All right, then you get to the magnification, the 10x objective, and most people think that's the most important number up there, and I will argue it is not the most important number. The next one is. The numerical aperture is the number that comes directly after it. So this is a 10x, but it's a 0.30 NA objective. When you're dealing with any kind of magnification at all, that's the most important number, because that's the number that defines the resolution of your system. The higher that number is, the better your resolution. Resolution is defined as being able to identify two little dots as being two little dots. They don't blur together. In standard light microscopy, the closest you can get theoretically is about 200 microns. You can't get that with a 0.3 NA lens. You might be able to get to it with a 1.4 NA lens, but not a 0.3. So, for instance, on my confocal, my highest magnification lens that I use is a 63x objective. And people say, don't you have 100? Well, I do have 100, but they're both 1.4 NA lenses. All right? So they both have the same resolving power. And by using the 63x objective at 1.4, I give myself a bigger field of view, and I can zoom into areas and give myself more flexibility. If I'm dealing with a 100x objective at 1.4, I'm getting the same level of resolution, but I'm limiting and I can't go out to as big of a field of view anymore. So anyway, so that's the more important number. The tube length, that's where the infinity symbol is on old you know you have an old microscope if that says 160 or 170. And if you do, that's an objective that only works on specific microscope bodies. All right, it won't work on a more universal platform, but we just kind of explained infinity, so I'll go on. Working distance, as I said, with the 10x objective, that working distance is massive, 15.2 millimeters. So you got a huge distance, right? So you're not going to be hitting anything if you're not looking. So that's why you start with the 10x. The color band, this is kind of generic, but for the most part works. The yellow, as I said, is going to be on a 10x objective. Your 20x is going to be green. Your 40x is going to be blue. Now, if you got a 60 or a 63x, it's going to be a slightly different blue. If you've got a 100x, it's generally going to be white, but that's an immersion lens. We don't have any of those today. We're not doing any immersion stuff. If you go underneath 10x down to like the 4x or 5x, you're going to have a red band. All right. So especially if you're doing fluorescence and it's dark and you can't read the numbers on there, go for the color band. Right. This is it's kind of a silly thing, but it's very important. When you take your slide and it's got a cover slip on it, you want to make sure that the cover slip always faces the objective, because the objectives are designed in the factory. All right, again, there are exceptions to every rule, but in general, they're designed at the factory expecting to look through a 0.17 millimeter cover slip. That's standard. If you happen to take your slide and you turn it upside down, all right, you've got a thicker piece of glass now, right? All right, now, if you got the 10x objective in there with the big working distance, you're not going to see a difference. Everything's going to be fine. But when you dial in the 20, guess what? That glass is too high, and you're going to hit it, all right? So you always got to make sure the cover slip is on. And the only way to make sure the cover slip is facing the objective is to feel for it. Make sure that you feel the edge of the cover slip. Okay, yeah, I've run into issues where people have had two cover slips stuck together. That creates problems too, but we'll just move on. That's a special case. All right, clean. Everything's got to be clean. In a transmitted system, which is what we're talking about first, standard bright field imaging, any glass in the entire system has the ability to have dirt on it, have dust on it. Now, how many people in here wear glasses? It looks like a lot of you wear glasses or contacts or something like that. All right. All of us, at the end of the day, at least once in our lifetimes, if not at least several times a day, have said, oh my God, was I looking through those? All right? All right. Your eyes accommodate. They get used to what you're looking at. They get used to the garbage. But the camera never does. The camera's going to show you everything. So you want to make sure everything is clean. The top of the slide, the bottom of the slide, the objectives, the condenser, the field, everything, right? So I'm not going to have you guys cleaning all this stuff because that's a whole other talk. But just keep in mind that those things do come into play. And the one thing you do have control over is your slides. So make sure the slides are clean top and bottom. As an example, we have this thrips here, and you can see there's all kinds of garbage on there. And if I focused up and down, I realized, heck, a lot of that garbage is on top of the slide. So what I did was I cleaned off the top and the bottom, and voila. Isn't that a better picture? All right? So go make sure everything is clean. One of the reasons I don't really want to have you guys going through the cleaning process is because of this. Everybody thinks when they're cleaning their objectives and stuff that they're cleaning the glass. Guess what? You're not touching glass. There's no glass there. What you're doing is polishing metal. That's because on the surface of all of these glass surfaces, you have a metallic anti-reflection coating. It's only a couple molecules thick, and if you scratch through that, guess what? It's permanent. You can't get it back. So yeah, well, that's why if you look at a really old objective, they look really horrible on the top because people, were cleaning them with all the sort of wrong things. What do I mean by the wrong things? Okay, how many people, in a lab have noticed that little green box in the wintertime when you had a cold and you needed to find some tissue someplace? Below your nose. All right, how many people, tell me, come on, hands? All right, well, only a couple are admitting to it. But what you'll discover is that after 2 times of blowing your nose, sometimes even 1, you have ripped the skin off the bottom of your nose and it's horrible, right? Why? Because this is low quality paper. This low quality paper still has lots of sand in it that they use to grind up the fibers. This is sandpaper. Do not use sandpaper on your lenses. All right, so you never use Kim wipes on any glass stuff. Well, any microscope glass stuff. It's okay on slides generally because you're only using them once or twice and there's no coatings on them. All right, yeah, so what you would use is a blower brush or an air duster, being careful not to expel the propellant that's in the duster. Cotton swabs with and not Q-tips, by the way. Q-tips have like nylon, I think, in them, or they have some polyester or something. It's not all cotton. You think it is, it's not. You want to use only cotton swabs, and so like Puritan brand cotton swabs, for instance, are on a nice long wooden stick, and that's what we get. You're going to use lens tissue only for cleaning lenses. So this is for when you go back and work with your own, not this one. DI water makes great, or your breath makes great DI water, distilled water. Just go, and there you go, you got some. Ethanol is the other kind of go-to thing if you want to clean most things that you might find on a slide. Windex actually works pretty good too, although Sparkle is better than Windex if you have access to that. Let's get down to the substage condenser. So basically what we're doing is we've started at the top and we're kind of working our way down through the bright field system, kind of in reverse order of the light path. So we came through the lenses, we just talked about the stage, and oh, by the way, why do we use Kim wipes? Kim wipes are great for cleaning things like the stage. You get stuff on that, Kim wipes are fine, the external surfaces only. All right, so underneath the stage we have the condenser setup. Now, depending on which microscope you're looking at, some have more controls, if you will, than others. And so, for instance, Jim's inverted scope has very little adjustment that you can do in the condenser system. It's kind of fixed. You can put the phase ring in and out, and that's about all you can do. But everything's essentially fixed in place, and everything is basically in its correct location. However, if you're more like me and you want to be flexible and you have different things to play with, you need more controls. So we have a turret that's down here, we have an aperture, we have the centering screws, but this whole thing down here, its main purpose of the condenser is to take the light that was coming down from that main light source and focus it at a particular place in the light path. Without getting into what the back objective focal plane is, the point is that the condenser is focusing it someplace. And it's got to be in focus at that place in order to get good results. So we have to talk about doing that. So again, just showing you the parts. On a condenser, you're generally going to have some kind of a turret like this. You'll have an A or an O for aperture or open. It's kind of the same thing. And then maybe a 1, a 2, a 10, who knows what's on there, all different things. You just have to figure out for each scope what it is that's there. But the A stands for aperture in this particular case. Now here, this is fun. Go to, let's say, 3 different textbooks on microscopy and see what they call that aperture there. Some call it the condenser aperture. Some call it the condenser diaphragm. Some call it the aperture diaphragm. It's all the same damn thing. Excuse me, I didn't mean to say that. But anyway, personally, I think that's sort of redundant. And I generally call it the condenser aperture, but either way, it's the condenser that's, or the aperture that's in the condenser. Right. Remember, we have a focusing knob for the condenser. right? So that's going to be how we focus the light of the condenser. And then you have the focusing knob for the specimen, 2 different focusing knobs. We're going to play with both of those. Down here we have the field diaphragm. So the field diaphragm is where the light from the back here came through and up from underneath the microscope. Guess what? There's another, well, it's the field stop, and in there's another diaphragm. So it's the field diaphragm. Oh, there's that word. How many? All right. I know that the number of hands that are going to be raised here are going to be higher than in most times I ask this question, but true show of hands, how many people have ever heard the word Kohler illumination before? How many of you? Oh, good, a whole lot of you, but there are still a few who haven't, so we're going to go through the process. So to set Kohler properly, we're going to need all the little things that we were just talking about, all right? All right. Kohler illumination kind of starts with the field diaphragm. Oh, I know, yeah, we're not quite to Kohler yet. I'm talking about the field diaphragm. What does the field diaphragm do? This is a little demonstration that I made years ago, and I think it really kind of helps explain what the purpose of the field diaphragm is. Well, maybe not all of us, but lots of us used to shoot slide film, and we had a big light box, and you would take your slide and you'd put it on the light box, right? So here, let's put a slide on the light box. All right, you're looking at the slide on the light box, and all this light is getting in your eyes. Oh my goodness, I can't see anything, right? So it's difficult to see. And what's happening is all that extra light is bouncing around in your eye or through the system and kind of filling in the shadows and lowering your contrast and doing nasty things to your image. So what do? You take some black card and you basically cover up all the white. And now you have a nice clean image of whatever your slide was. You don't have all that extraneous light in the way getting in your eyes, and you can get a much sharper, better contrast view of your sample. That's what the field diaphragm does. And if you think about it, every objective has a different field of view, right? A 10x objective is going to see this much. A 40x objective is going to see this much. So that means every time you change the objective, you've got to close that diaphragm up or down so that it matches the objective. That's going to be part of what Kohler is. All right, we're going to come back to that in a minute. So most people, and you're not most people, but most people, when they first learn how to use a microscope is probably in a biology class someplace. And it's usually in college, and it's usually in a room full of 200 or so other people. And you have some grad student going around, okay, all right, here we're going to show you, here's the scope, you look here, you turn it on there, you focus there, any questions? Good, okay, next. And that's all of the training they ever get. And so what people think they're doing is they look through and say, ooh, it's bright, it's way too bright, so let me turn the light down. So what do? They turn the light down by turning the voltage down. Well, there's a problem with that. When you turn the voltage up or down, you're changing the color balance. And so that's going to change the way your pictures look. So anyway, generally on a microscope, you're going to have a voltage knob, but look very closely at the combination. There should be some place where it's saying this is your photo position. And if it doesn't, pick one. The best place is all the way on. It's reproducible. You always get to the same place, all right? Someplace in between is a little more dicey. It's usually around 12 volts. Could be 10 volts on some of the older ones. But either way, when you turn on your power, there's going to be a power switch, but then you've got the voltage knob. You turn it on, you leave it alone. This is an example of what I was talking about with the voltage. This is an unretouched picture of a white space, okay? So I focused on an area. I had the voltage set sort of at a mid-range. I color balanced to that mid-range, and then I turned down the voltage and took a picture. So when the voltage was higher, this was white, all right? But that's the picture I got when I turned the voltage down. Then I turned it all the way up in the other direction, and that's the picture I got, all right? It's that much of a difference. That's how much the color balance shifts as you go through the whole voltage range. So if you can't turn the light up and down by changing the voltage, how do you make it brighter or darker, right? Well, you look for little filters. So we have neutral density filters usually somewhere in the light path that you can put in or take out, and those will attenuate how bright or dark your image is without changing the color balance. That's why they're called neutral density, All right? So you put them in and out. Now there's also going to be, usually where you've got filters, you're also going to probably have a blue filter. That's fairly common in most microscopes. There's a blue filter in there. Nikon calls it an NCB11. It's a neutral color balance filter. Again, this kind of harkens back more to film days, where if you had daylight balanced film or you had tungsten balanced film, you're using a tungsten light source most of the time. And so if you use tungsten balanced film, you're perfectly fine. But if you put daylight film in, which most film was, you needed that blue filter in to color correct for the difference in the quality of the film. These days, we're using digital photography instead, and you can do a auto white balance in the software, and it doesn't really matter if you've got the blue filter in or not. All right? You can always hit the white balance, and just whatever it's at, that's what it'll balance out for you. So you don't really need the blue filter, but just by convention, most people are used to looking through it, so keep it in. So that's kind of what I was talking about with the neutral density filters. You can use them in combination. You can put 1 or 2 or 3 or that one, the first one and the third one, or if you only got 2, whatever. They're neutral, so you can kind of stack them and adjust just how much darker or lighter you want. So making them a denser set of filters is going to make the image darker, meaning you'll need a longer exposure out of it. If you open them up, you're going to burn your eyes out, but you can get a much shorter exposure out of it. It really kind of depends on your comfort zone, really. So bright field microscopy is basically your standard. Everything kind of starts with this, right? And again, I've kind of shown you this before, but these are the basic parts. You got a condenser down here shown with the aperture open. You got your specimen, you got your objective. The light is going to transmit straight through the whole process. There you go. Got your image, all right? Everything's fine. You're going to get pictures like this. This is an H&E slide of a liver. This is the liver triad area. So you got a hepatic portal, you got some hepatic veins, you got some bile ducts, you've got some hepatocytes out there, red blood cells. It's kind of cool. All right, so anyway, but that's your basic H&E hematoxylin and eosin slide. All right, so here is basic operation 101. Put your slide on the stage. Where's the cover slip go? Well, unless it's on the inverted scope, in which case it goes down, right? Toward the objective. All right. Turn on your lamp. Optimize your voltage. Leave it alone. All right. Whoops, backing up. Use the neutral density filters instead if you need to adjust the brightness. All right. I didn't mention before, but the oculars generally have an inner pupil area adjustment so that some of us have eyes that are like over here and some of us have eyes that are here, so you can adjust that as you're looking through. So adjust your inner pupil area distance and focus the oculars to what you think is correct. Then focus your specimen. Hey, fairly straightforward. And then there's the biggie, set Kohler illumination. Now, I did not spell it properly, and I'm not even pronouncing it properly. Sorry about that. It's actually pronounced Köhler illumination, and it's a K with an O with an umlaut on top, but I never know how to make an umlaut in PowerPoint. So anyway, the bastardized American way of saying it is Kohler illumination instead. Of course, Köhler was a German, so that's where this comes from. So with bright field, Kohler is the point where everything is in focus where it's supposed to be, and we need to start at that point. So it's our basic starting point. The proper setting is going to ensure that everything's where it belongs, right? And it needs to be adjusted or checked every time you change the objective. Like I said before, just that one part when you're thinking about the field diaphragm, if I'm at 10x and I have the field diaphragm this big and I put in the 20x, I need to make sure I close that down. And adjusting the field diaphragm is part of Kohler. Okay, so what's going to happen is we're going to basically focus that uneven light source at someplace else that's not the specimen plane. Because if we focus that spiral filament at the same place that the sample is, your picture is going to be bright, dark, bright, dark, bright, dark. So how the heck do we get even bright illumination, right, without, from an uneven light source? What we do is we focus it at a different place. So the light path focuses at a different place than the imaging path does. So focus and center the field diaphragm. So by doing this, we're going to make sure that the condenser is in the right place. We're going to then adjust the condenser diaphragm. And hey, guess what? That's it. That's what we're doing when we do Kohler illumination. It takes forever to explain this stuff, but we're really only doing those two things. We're focusing and centering the field diaphragm, and then we're adjusting the condenser diaphragm, okay? So this is how it works. You're gonna put your slide on and focus on your sample, right? We opened the field diaphragm to begin with, right? Right. We have our specimen in focus. It is now in focus when we're looking through the microscope. And we're going to take the field diaphragm and we're going to close it down. Now, if it's not in the right place, it's going to be blurry. If it's not center, it's going to be off to the side. So we close down the field diaphragm, right, until we see basically a circle of light and dark around the outside. Then we have to focus the condenser to get the edges of this sharp. Now, centering the field diaphragm, like I said, if this whole circle is up to the corner, you use the little centering screws underneath to move it to the middle. Right? And then you open the field diaphragm. And that just makes sure that you open it up until it just disappears from the field of view. Right? So it doesn't become part of your picture. But what does all this mean? It means that the image of the field diaphragm here is going to be in the same plane of focus as your specimen is. Right? So your specimen and the field diaphragm should both be in focus. That's the key. All right, so I think that's kind of what all that just said. Yeah. All right, now, we now in this example have opened up the field diaphragm and it's just passed. I mean, it would be a circle, you know, kind of like out here, right? And we see our image. Now, in our 2 steps to do Kohler illumination, that was focusing and centering the field diaphragm. Now we move to the second thing, which is setting the condenser aperture. Right? And when we do that, we're going to look at the difference between these two. Can you see much? It's kind of hard to see. It's a little, yeah, one's a little more contrasty than the other. And so by closing down the condenser aperture, condenser diaphragm, think of it like squinting. You know, like when you close your eyes, what are you doing when you're closing your eyes down? What's happening is light from a distant part is kind of coming through your eyelids and it's getting refracted a little bit. It's getting bent and it's sharpening the edges of what you're looking at. That's why when you squint, things around the edges look a little bit sharper, right? Now what happens if you squint too much? You close your eyes, right? And you can't see anything. So obviously everything in moderation. If you go too much, you kind of mess things up. So there's a sweet spot. You can see it a little bit better here at higher magnifications. Lower magnifications, it's not as obvious. Higher magnification, it is. On the left, this is actually correctly set. We have fine detail in here, and over on the right, it's closed down too much. You can see this edge is what I call refractal. You can see like little dark edges to everything. Now, it might make for a nicer contrasty picture, but I tell you, I did a workshop once years ago for the USDA, and we were doing some of this stuff on pollen, was it pollen grains? I think it was pollen grains. They were identifying pollen grains. And there were these 2 particular types. They looked identical, all right, except that this pollen grain could be led into the country and this pollen grain could not. Right, so they were identifying the different types of plants that these were coming from. The only visible difference between the 2 was this one that could not be led into the country had a double membrane on the outside, and the other one did not, had a single membrane. If you close down the condenser aperture too much on a single membrane, it turned into 2. Right? It got overcorrected. So that's what I'm saying. You can get to the point where you overdo it. Right? So if it gets too refractal, I'd back off a little bit. All right. So that makes a lot more sense when you're sitting in front of the scope and adjusting it. I have a few slides here to kind of show some different other things that we are going to have available to us. So when you're looking through a microscope, basically you need to enhance something to be able to see it and take pictures of it. So what can we do to do these enhancements? Well, for bright field, you know, if you section a piece of tissue and you put it on a glass slide and you look at it, what color is it? It's kind of like Scotch tape on saran wrap. There's nothing there. There's really no color. So what you get is you get your colors by staining. So that's one way to get color anyway. So H&E, hematoxylin and eosin, is your basic color stain in pathology, right? And so that's what a lot of these slides are going to be. So tissue staining gives us color. Now H&E isn't the only stain. There are other stains. So we can see, you know, specific things. There are also some optical enhancements that we can do. Dark field. Again, Jim showed you an example of dark field before. I love dark field too. It's a great technique. And anybody can do it with a regular camera or with a microscope, because all you're really doing is you're putting your sample here, right, where I am right now. You're focusing on me. And what do you see behind me, right? You see light, because you see that's up there. Now, what if instead we put black directly behind me? What are you going to see? I'm going to be outlined against black. And then you take the light from, instead of coming straight through me, you have the light bouncing off my sides. So you have the light coming from here and here instead. So now what you have is this nice rim light all around me, and it's black directly behind me. That's dark field, right? And you can do that very simply in the microscope. And what Jim showed before with the stereoscope is one of the easiest ways to do it, because you know you've got these big gooseneck lamps, or you've got light underneath that comes through another stop where the light's coming from the sides instead. So it's great stuff. So dark field microscopy. This is basically how it works. Remember the bright field approach that I showed you before. This is dark field. So with dark field, you've got your objective, you've got your specimen, and now you've got this. Instead of a straight path through underneath, you put an opaque stop in the way. It's got to be the right size, but it's right there. And the light is going to come up from underneath and cross over, and none of the light from here is going to make it into the objective, right? And directly behind the objective, you just see black. So that's what's happening. We're lighting up the edges of the specimen, and then that's the light that goes up into the objective. That's how dark field works. Now, what can you do with dark field? Let's take an H&E section and look at it with dark field. That's kind of cool, right? So if you want to play a little bit, this is actually the first picture I ever sent into the Nikon Small World competition. Very first picture I ever sent. I got 7th place many years ago. And that was just playing with a demo scope, by the way. So that's the importance of demos. Anyway, here's an example of a mite. No, it's not a mite. Yes, it is a mite. It doesn't matter. I can't remember what it is. This is from the USDA stuff again. On the left, we have the bright field view, light coming straight up through. On the right, we have the dark field view. Notice we can see this nice blue belly band here, the muscles across the belly, that you can't see over here, right? So you can use some of these techniques to see things that you wouldn't see otherwise. But this is not stained on the right. It's only, the contrast adjustment is coming from the optical enhancement that we've done. Now, the one thing about dark field that's really critical is everything's got to be clean, because you get all this crud showing up just as nicely as your specimen. All right, what else can we do? We can do phase contrast. You have an objective in your specimen. The thing that makes phase contrast work is that you have 2 stops now. You have one underneath and one above. And you see what happens here is the light from what looks like a dark field stop comes up, crosses over, but this time it's a smaller stop. So some of the light does make it into the sample. But now I have another stop that's up inside the objective that matches that one. It's the opposite of it. One's the light stop, one's a dark stop. And so the light that's directly goes through hits the dark stop. And so now what's happening is you're going to have the light that's refracted from the main light here is going to come on up through, and that refracted light's going to form our image. What does that look like? Hey, good old buccal cell, buccal epithelium. Take some scrapings from the inside of your cheek. Again, Scotch tape on saran wrap. If you're looking at it with bright field, pop in that phase ring and instant contrast. Right? As long as you've got the right one. Our mite looks a little interesting too. So basically, when you're looking at phase, what you have is this sort of light ring around everything. So there's a light edge, but the background is gray, it's not black. DIC, again, buccal epithelium with and without. DIC is a differential interference contrast, also called Namarsky. And it basically gives you sort of a pseudo 3D effect, right? So this is much more complicated to talk about. There's basically 4 parts to it. You have 2 prisms, and you have 2 polarizers. So one of each above and below the specimen, and that's kind of how it works. I'm not getting into the specifics, but we can set it up and you can look at that. Our little tick guy or mite or whatever he is looks like that when you look at it in DIC. I mentioned part of DIC is polarization, right? And because of polarization, hey, guess what? We've got a chitin out in the edges of the little clipper things there, and that's why those show up bright. So we got polarizers, so we can do cross polarization if we don't put the prisms in. So that works too. All right, so basics of using any microscope, never force anything. All right, if you're trying to focus and it's like, oh, it's not going, do not go another chunk. That's when you hear that famous crack, awful sounds. You know, you don't want to hear those noises. So never force anything. Something's probably in the way. Figure out what it is or get some help. Never touch any glass surfaces with your fingers, right? You really want to be looking through dirty fingerprints. But ethanol does clean that off. But again, I don't want you guys cleaning it. If you do find fingerprints, let us know. We'll clean it. Never, 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 never. All right? No Kim wipes. And always start with the 10x. I beat that one to death. I mentioned at the beginning of the talk that magnification is always sort of one of those things about me. People will say, oh, it's 400x, or it's 100x, or it's 200x. Well, to what? All right? In the old days, you could figure out magnification to a 35 millimeter piece of film. All right? But if you really want to go with that model, you need to figure out how big it is on the chip. Right? And all the chips are different. Right? And then another way people do it is they'll take the objective, say 10x, and the oculars, also 10x, and they'll multiply them and say 10 by 10, that's 100x magnification. Well, it's 100x magnification virtually to your eyes, but again, how big is your picture, right? So bottom line is there's too many darn variables. Nobody can agree on it. So if you want to know what the magnification is, you take a picture of a scale. Hey, scientific photography, scales everything, right? So you have a stage micrometer, and it's got graduations so that you've got the small marks here are 100 micron intervals, and these are 10 micron intervals, and you can go bigger than that as well. I think it's 2 millimeters total. But that's how you do it. You take a picture of your sample, you take a picture of the stage micrometer with the same conditions, and then you know how big a bar will be on your final image for your magnification. So you say bar equals 100 microns, and now you know your magnification. And from that, you can measure something. So that's basically it. Okay, time to play. All right, thanks.